Thank you all for finding the time and visiting today's webinar. My name is Lily Wang. I'm a professor of statistics at Iowa State University. I'm one of the committee members of the COPSS-NISS COVID-19 Data Science webinar. It is my great honor to be the moderator for today's webinar. Our topic today is transmission dynamics of SARS-CoV-2, inference and projection. The current COVID-19 pandemic has resulted in the unprecedented development and integration of infectious disease dynamic transmission models into policymaking and public health practice. Models offer a systematic way to investigate transmission dynamics and produce forecasts of infectious disease incidents at the population scale. We have two amazing world experts today, Professor Jeffrey Shimon from Columbia University and Professor Ronnie Rosenfeld from Carnegie Mellon University. They will talk about the application of dynamic model systems and model inference frameworks in the study of SARS-CoV-2. So here's the format to give you an idea of what to expect in this webinar. First, Professor Shimon will give a 20 to 30 minutes talk. Then Professor Rosenfeld will provide about 10 to 15 minutes discussion. Then Professor Shimon can have a few minutes to respond to Professor Rosenfeld's response. And then lastly, we'll have the rest of the time for Q&A, depending on how much time is left. And for the audience, you have the opportunity to submit the test questions by typing your question into the QA panel. You may submit the questions at any time during the presentation. We'll collect these and address them during the QA session at the end. So now I would like to introduce our first speaker today, Professor Jeffrey Shimon. Professor Shimon is a professor in the Department of Environmental Health Sciences and director of the Climate and Health Program at the Columbia University Mailman School of Public Health. He studies the survival, transmission, and ecology of infectious agents, including the effect of meteorological and hydrological conditions on these processes. Before the COVID-19 pandemic, his work has primarily focused on mosquito-borne and respiratory pathogens. He uses mathematical and statistical models to describe, understand, and forecast the transmission dynamics of the disease systems, and to investigate the broader effects of climate and weather on human health. Okay, now without further delay, I will turn the time over to Professor Shimon.
Thank you, Professor Wang, for the introduction. It is a pleasure to be here. I'm going to share my screen so we can all partake of the slide deck that I will work from. Let me just do this, and this, and this. So I am going to be talking today about the transmission dynamics of SARS-CoV-2, which is the causative agent of COVID-19. And I'm going to be discussing some modeling work that we've done that has supported both the inference and projection of this pathogen, and really be focusing actually primarily on the inference. I'm just going to acknowledge some of the funders that have supported this work. If I don't do it early, I forget to do it at the end, as well as some of the collaborators who have contributed to this in various ways. In particular, I want to point out Dr. Sen Pei and Dr. Marta Galanti, who work in my group presently as associate research scientists and postdoctoral scientists who've done a lot of the spearheading of some of the work you're going to be seeing. So before I get into modeling, I want to actually take a detour into some basic biology, virology, and epidemiology. We had a project that we titled the Virome of Manhattan that was funded by DoD that allowed us to look at respiratory viruses in a way that hadn't really typically been done. The way that respiratory viruses are typically surveillanced is through a passive system, and that is, in order to know what kind of viruses are circulating, we wait for people to seek clinical care. They come into a clinic or a hospital and they present with symptoms that are consistent with a respiratory illness, something like a fever of 100 degrees Fahrenheit or greater and a cough or sore throat specifically. they will be slapped with the label influenza-like illness. This is a syndromic surveillance diagnostic that tells us that there's a fraction of the population who are seeking medical care who are manifesting with symptoms that are consistent with a respiratory infection, specifically something that's influenza-like. In addition, some of those people who come in may also be swabbed. They may get a nasopharyngeal swab, and that may be taken to the lab and actually tested for various viruses. Sometimes it's just flu, sometimes it's flu and respiratory syncytial virus. Sometimes it's a broader suite of respiratory viruses that will be interrogated. Because the system is passive and because this is standard surveillance throughout the world, we only have a window into those infections that are acute enough that they're causing the people infected with them to seek medical care. And they don't give an overall assessment of the true burden of disease imposed by these viruses, their overall prevalence, the lost days of work, and the amount of symptoms that they are causing. So to look at this and try to understand just how prevalent these viruses are, as part of this Virus of Manhattan project, we set up a couple of field arms. In one of them, we sampled at a common tourist attraction in New York City, and we would ask people to give us a medical history, to tell us what their symptoms were vis-a-vis 9 common cold symptoms, things like runny nose, watery eyes, cough, sore throat, chills, sneezing. They would rate those on a Likert scale, none, mild, moderate, severe. And then we would take a swab of them, regardless of how they felt at this tourist attraction. What we could see from that is, having taken those swabs back to the lab and tested them for 18 different common respiratory viruses, that there are a lot of people walking around at a major tourist attraction, adults, in a place like New York City, who are shedding respiratory viruses. In fact, in February, in the month of February, when we did that, we did it multiple months, but in February, 1 in 9 persons was shedding a common respiratory virus. Now, the other arm that I want to talk to you about of this study was a cohort that we established in which we asked people to keep a daily diary or log of their common cold symptoms. Those same 9 symptoms on that same Likert scale, they would enter over their phone into an electronic database that we maintained on a daily basis. It took all of 30 seconds. In addition, they would also tell us if they had stayed home from work or school because of their symptoms, taken medicine because of their symptoms, or gone to see a doctor because of those respiratory symptoms. And so what we were able to amass over a 19-month period with 200 plus individuals was a time series record of symptomology and behavior in response to that symptomology, daily record of it. In addition, once a week, regardless how any of these individuals felt, we would get a nasopharyngeal swab from them and take it back to the lab and test it for 18 different common respiratory viruses. So at the same time, we're building up a time series of infection. What we could see from this is that there are a lot of infection events that were manifesting in this population, which included toddlers and preschools and daycares, people who worked at the medical center, in pediatric and adult EDs, and as well as high school students and teachers. And we could see that there were a lot of respiratory symptoms and a lot of respiratory infections. In the table here, we define episodes, and an episode is a group of consecutive weekly specimens from a given individual that were positive for the same virus while allowing for a 1-week gap due to false negatives in the testing or temporary low shedding. So we tested for 18 different viruses. We've grouped them here. So influenza A and B are in the same group. RSV A and B are in the same group under RSV. If somebody had to have just RSV A, they couldn't switch between them to be considered a single episode. And what you see is over the time period, we had roughly 30 episodes of flu, RSV, and parainfluenza, 20 of human metapneumovirus, 275 of rhinovirus, 63 of adenovirus, and 137 of the endemic coronaviruses. This is all before SARS-CoV-2 emerged. The next column, MA, designates medical attention. These are people who sought medical attention for their respiratory symptoms during these episodes. And what you can see is the numbers are much lower. If you go to the next column, it shows the probability of seeking medical attention, given that you have a particular viral agent. And what you can see is that in that column, the highest probability lies with flu, but it's less than a quarter, meaning less than a quarter of the people who had an infectious episode with flu sought medical attention for that infection and for those symptoms. And it gets down to as low as 1 in 25 or 4% for the coronaviruses. If you go further to the right and you see what fraction stayed home, you see it's less than 50% in all instances. And if you look at what fraction actually took medication, you see it's also fairly low, less than 60% in all instances. So what did this tell us? It told us, firstly, that undocumented to documented is actually a natural dividing line to look at, because the people who don't seek medical attention, we don't know if they're actually incapacitated by it, if they have just mild symptoms, if they have no symptoms. We don't know what the range is, but if they don't seek medical attention, they're not going to be found. Secondly, we see that what's happening is that the majority of people who get these infections, including for something as severe as flu, do what you or I do in the wintertime when we get a sniffle or a little body ache or a little chill. And that's nothing. We still go to work, we still go to school, we still get on planes and take business trips or go on vacations, we'll go out to dinner, we'll go shopping. We take the virus out with us, and we are shedding the virus. And it's this property that allows these viruses to persist. It's what allows them to get around, because people are unknowingly sharing these viruses. Okay, so in January of last year, we were watching as we see reports of COVID-19 in China, and we see how rapidly it's spreading amongst the population there, and then hopping on airplanes and going to Thailand, and then Japan and South Korea and the US. And we immediately are struck by the rapidity with which this novel agent, unlike some of the other ones that we've seen previously, such as H7N9, H5N1, which are both flus, or SARS-1 or MERS, unlike them, this is moving very rapidly, and it's causing infections in a lot of locations, and it's cropping up in geographically distant areas. We immediately reflect on the things that we've learned from this Virome project, and we suspect that there is a tremendous amount of undocumented infection associated with this virus, and this is what is supporting its ability to spread within communities and between communities. So we set up a model system to try to quantify this. What we did is we built a metapopulation model that represented the transmission of the new pathogen within 375 cities within China. And we used 10-cent travel data, which is a location-based service that records movement off of iPhones, and it's embedded in very popular apps within China, such as WeChat and QQ, to document the movement between those 375 cities in the run-up to the Chunyan Spring Festival, the Lunar New Year. We took this model and we coupled it with data assimilation methods. These are Bayesian inference algorithms, and in this case, it's going to be the ensemble adjustment Kalman filter. And we're going to use that in conjunction with that mobility data and daily observations of cases from all 375 cities. Now, those cases are the documented infections. We're going to take it and we're going to simulate the virus within these cities for a 14-day period and use that to support inference of key parameters within the model that guide the transmission dynamics of this pathogen. We use this period from the 10th to 23rd specifically because prior to the 10th, there is not that much virus to detect. The cases are very sporadic and it's not going to provide as robust a signal. We ended on the 23rd because that was the day they imposed lockdown on Wuhan City, the epicenter of the outbreak, which was quickly spread and enforced in much of the rest of China. And ultimately, within a few days, had about 750 million people within the country under lockdown. Now, that prior to travel restrictions is important. We do this prior to the travel restrictions there because this shows us how the virus spreads unencumbered in Chinese society as they normally interact with one another. Now, within the model, we separately represent documented and undocumented infections using that dividing line that we observed so well in the Virome of Manhattan project. In addition, we model has separate contagiousness for both the documented and undocumented infections. It allows them to spread differently per person per day. Now, before we're going to use this model, which we're going to simulate and combine with the inference algorithm in order to estimate critical parameters within the model, and there are only 6 parameters within this model, which is nonlinear, we need to understand whether or not the system is identifiable. So the way that we approach this is that we do a bunch of synthetic tests where we take the model in free simulation, impose initial conditions and parameter combinations for it, run multiple stochastic outbreaks, and then take each one of those outbreaks and feed it into the full model inference system and see if it can reconstitute, that is, estimate each of the parameters reliably. We do it over and over again, as I said, for different parameter combinations and initial conditions, and we see whether or not this system consistently find the right answer. What you see on the left is one example of that for the 6 parameters. Beta is the contact rate. Mu is the relative transmissibility of undocumented infections relative to documented. Theta is an adjustment of the travel from the 10-cent data, because we recognize it's going to be an undercount because not everyone uses that, has that location-based service on their phone, if they have a phone. Z is the length of the latent infection period of the virus. Alpha is the ascertainment rate. It's the fraction of individuals who are infected who become documented or confirmed cases. And D is the infectious period, how long a person is contagious on average. And what you can see here is the red show the truth, the blue shows the 95% credible distribution, actually it's the full distribution of the estimates, and you can see that we're capturing within those span of the estimates there what's going on. Now, we did this over and over again. We even then did it for subunits. We saw that if we got under about 20 cities in our model from the 375, we were no longer able to identify what was actually going on. But we did it enough to satisfy ourselves and ultimately reviewers that the system was identifiable. And we then applied it to the actual data. And this shows you the estimates of the 6 parameters plus the basic reproductive number, which is a hyperparameter based on 4 of the core parameters. I want you to focus on 2 of them, the reporting or ascertainment rate alpha and the relative transmission rate mu. What we see is that the reporting rate alpha is 0.14. That means that we estimated that 14% of infections during this 2-week period were being documented. And mind you, China had diagnostic tests and they were using them aggressively at this point. Furthermore, that means that 86% of the infections that were taking place were undocumented, so roughly 6 and 7. Then mu per person, it indicates that per person undocumented infections are on average half as contagious, roughly 55%, as documented infections. We also got an estimate from the hyperparameter of 2.38 for the reproduction number, and that was in line with other estimates from that time period when we did this in January and February. We then take the model with the parameters and we actually run it in free simulation. This is 1,000 simulations with that, and see whether or not we're capturing the distribution with our distribution of our runs, some of the key features that actually manifest. And what you're seeing here is the simulations as box and whiskers on each day, and the observations are shown there as well. And you can see we're seeing the growth in cases at the national level, in Wuhan City specifically, in the Hubei province in which Wuhan City resides. And you can see the estimates there, again, of the reproduction number. On the lower right, it shows you our estimate of the number of cities that will have cumulative incidence of 10 or more confirmed cases over time. And you can see that we're able to capture that as well. Now, because it's a model, we can play around with it a bit. And we said, all right, well, we're seeing that the undocumented infections are in fact supporting the rapid spread of this disease, but how much so? They're half as contagious, roughly. It's a model. Why don't we shut that off and make that 0 and see what happens to the outbreaks? Are they of similar character or are they greatly affected? And what we can see, if you look at the blue box and whiskers and compare them to the red, which is the one with the actual estimates, that we have a greatly attenuated outbreak. As a matter of fact, roughly 80% of the confirmed cases no longer develop when we run it, where we no longer allow undocumented infections to be contagious. So what does this say? It says indeed that the undocumented infections, people who are unaware, most likely, that they have this virus and may not even have symptoms, they may be asymptomatic or mildly symptomatic, that's called paucisymptomatic, or maybe they're just toughing it out at home. They are undocumented and they're unknowingly spreading this virus to other people. They're getting on rapid transport, they're getting on airplanes, and they're spreading it around the world. I'm not going to show it here, but we also were able to demonstrate that there was evidence of pre-symptomatic shedding, and that it was roughly about 2.5 days prior to the onset of symptoms for those who do become symptomatic and are confirmed cases, they begin shedding the virus. So what it means is there are many opportunities to spread this virus. Now, if we look at other coronaviruses that have impacted humans, we know that there are a couple that emerged recently that were very concerning. One was SARS-1, severe acute respiratory syndrome, that emerged in 2003. It was highly virulent. It had a 10% case fatality rate, but it did not produce subclinical infections. There are almost none that have been documented. So everybody who got this infection was documented as having it, and furthermore, they did not appear to be contagious until their symptoms manifest. The other one that emerged recently was MERS, the Middle Eastern Respiratory Syndrome. This one was not as transmissible, which gets in the way of it. And furthermore, it only had roughly 1 in 5, 20% of cases of infections were mild or asymptomatic, i.e. subclinical. So it too could be circumscribed. On the other end of the spectrum, we have the seasonal or endemic coronaviruses, which go by these funny alphanumeric names you see here, like OC43. Those are the ones that cause roughly 135 infection events in that Virome project I told you. Greater than 60% of those infections that we documented in the Virome project were asymptomatic or mild, depending on how you define those. And only 4%, as I mentioned earlier, sought medical care, though interestingly, in all instances, they had either OC43 or HKU1, which are the beta coronaviruses, which is what SARS, MERS, and SARS-CoV-2 are as well. But what we can see from this is that this new pathogen lies between the seasonal coronaviruses and SARS and MERS. Really, it has 3 critical characteristics that allow it to get around efficiently. The first is it's a novel respiratory pathogen to which little of the population of the world appears to have pre-existing immunity, so almost anybody can catch it. Second, most of the infections that it causes are subclinical and are not going to be documented, and people who have those subclinical infections are not aware that they have them. They don't alter their typical behavior, and they spread the virus widely. Lastly, there are still a number of people for whom this causes severe complications and puts them considerably at risk of hospitalization, ICU time, or death. So when we did this, and we did this in late January, early February, we immediately realized that this was fated, unfortunately, to be a pandemic, and a pandemic of real consequence. So having done this for China, we did turn our attentions elsewhere. We turned our attentions to the US. First case in the US appeared around January 20th. It petered along at very low levels. And then, as you can see, right at the end of February, beginning of March, it began to take off exponentially. We built a similar model. In this case, the model was built at the county level. There are 3,142 counties in the United States. In each one of them, we have the same sort of metapopulation structure linked by Census Bureau travel records. We use those travel records to create movement, both work-related community movement and random movement between counties within the United States. And we performed a similar inference up through March 13th, which is really prior to when a lot of the interventions and non-pharmaceutical interventions went into play. What you can see here is we actually got very similar numbers as for China, except if you look at the reporting rate, instead of being 0.14, it's 0.08. And that difference is quite large. That means instead of 1 in 7 infections being confirmed, only 1 in 12 were roughly. That 1 in 12 jibes with the fact that there was limited testing capacity and restrictions on its use in the United States in the early portion of 2020. As a consequence of possibly having more severe infections undocumented, the relative transmissibility rises a little bit from 0.55 to 0.64. Now, since that first work, we've done various things. We've allowed some of the parameters within the model to vary through time, which messes with the identifiability, but allows us to get general estimates of some of the variability that takes place in space and time within the United States. We've used this to perform fitting an inference for the first wave through the beginning of May in the United States, where we allowed the contact rates to vary in counties that had 400 or more cumulative cases, hopefully a robust enough signal. We also brought in SafeGraph location-based mobility data instead of the static census data to allow for changes on a daily basis of travel within and between counties. This one I'm going to show you here spots like 6 metropolitan areas you can see there within the United States. We performed a fitting and inference to see whether or not we could capture it, and we can see that we are able to capture both cases and deaths at the national level through May 3rd, as well as it shows it just in this example for the New York metropolitan area. But what we can see is an estimate over time of the reproductive number, here measured as the effective reproductive number, and how there are different paths taken. New York starts pretty high, as does Boston, and they drop off at different rates. How New Orleans went down and then came back up again. How Chicago went down, but then never really quite got below 1. And they did have a problem in May that's consistent with this. And how the ascertainment rate varied over time from March 15th onward and was higher than our initial estimates in the early portion of the outbreak. We were able to take that same simulation and do an experiment and said, well, based on these things in the lower left here, which is the reproductive number, which is a measure of how it's changing because of all the non-pharmaceutical interventions people are putting in place. The policies that impose lockdown, the shutting of restaurants, the closing of schools, the mask wearing the public adopted, the compliance with social distancing, both the political and the public compliance with efforts to control the virus manifest as a reduction of that transmissibility of the virus. So we did a thought experiment and said, well, what would have happened if we had gotten our collective act together 1 week earlier? Done exactly what we did in the counties of New York the same way, but 1 week earlier. Exactly what we did in San Francisco County, which had the earliest lockdown, only 1 week earlier. Exactly what they did in a rural county in Iowa, where they did nothing 1 week earlier. What would the difference have been for that first spring outbreak? And we also tried 2 weeks earlier. And when we do this, we see a 50% reduction in cases and deaths with a 1 week earlier movement. And 2 weeks earlier, you get over 90% reductions in cases and deaths. It's not surprising. It's an exponential growth process. And if you jump on it earlier, you're going to be able to control it better. Now, I just have a few minutes. I'm going to tell you just a couple more things. This has really strong implications, we said at the time, for controlling what happens as we went into Memorial Day. That if we weren't careful and looked at things carefully and saw that there was a rebound beginning, as all the states were reopening in May, we were going to be overwhelmed and we were going to respond too slowly, and there were going to be outbreaks that got out of control. Now, obviously, we saw that in the summer in the Sun Belt, and more broadly, as we've gone into the winter and the virus has become more transmissible and people spend more time indoors, it's been even harder to control. More recently, we've done some work on vaccination now that they're out and they're deployed to see how well this will actually protect the population. The news isn't that great. The vaccines are a little bit late, given how much infection we've had here. In a place like Vietnam, where they've had 1,500 cases total and 35 deaths in a country of almost 100 million people, their incredibly stringent control of the virus, which has allowed them to actually have economic growth during 2020, means that they're very well positioned to reap maximal benefit from the vaccine and get the inoculant into people before they ever encounter the virus. In the United States, we're kind of late. And given the rollout that we're going to have, it's going to result in only a small aversion of the total number of cases that we're going to have during the current outbreak. However, it also means that we need to not relax the non-pharmaceutical interventions that are in place. Even though we haven't been controlling it well, it would be worse. And the current outbreak, which is probably beginning to abate, will continue to abate if we maintain our non-pharmaceutical interventions. However, if we don't, it will go up and even more people will be infected before we're able to get the vaccine in their arms. The last thing I'm going to say is that we've done an evaluation that we're going to soon be submitting of the epidemiological characteristics over the entirety of 2020. We've used seroprevalence data. These are surveys of antibody prevalence within hosts as a further confirmation of the model's estimation of what's going on. We provide estimates of the ascertainment rate over time, which has risen to about a quarter of the population now being documented, and overall cumulatively on average, about 1 in 5 cases, infections were documented over the course of 2020 in the US, we estimate. And we can see where we stand in terms of susceptibility in various populations at the end of 2020 here. And obviously, we're going to continue to monitor this going forward. So I will stop there. I thank you for your time, and I will certainly pass this on now to Dr. Rosenfeld as the discussant. Thank you.
Thank you very much, Professor Shimon, for a wonderful talk about how to use dynamic models of infectious disease systems to make an inference of undocumented COVID-19 infection and projection. And also welcome everyone who just joined our webinar. As a reminder for the audience, you can still submit questions through the QA panel. So Jeff, there are already questions in the Q&A. You may start answering the questions submitted while Ronnie starts his discussion if you think you can multitask. Okay, so now let me introduce our discussant today, Professor Ronnie Rosenfeld. Many of our audience have already been very familiar with him. This is his second time that he joins our webinar series. Professor Ronnie Rosenfeld is head of Machine Learning Department and Professor of Machine Learning, Language Technologies, Computer Science, and Computational Biology in the School of Computer Science at Carnegie Mellon University. He also holds a courtesy appointment at Heinz School of Public Policy at Carnegie Mellon and an adjunct appointment at the University of Pittsburgh School of Medicine. Ronnie is a world expert in epidemiological forecasting. He founded and directs the Delphi Research Group, which has won most of the epi forecasting challenges organized by the CDC and other US government agencies. Ronnie, we are so glad that you could be here today to be our discussant. Please take over.
Thank you, Professor Wang, for your kind invitation and for kind words and invitation. And thank you, Professor Shimon, for a wonderful, wonderful talk, which I really enjoyed. I realized that as a discussant, I can make things most interesting by disagreeing with Professor Shimon and pointing out weaknesses and problems. That would be the most exciting thing to do. But having known Jeff for almost 10 years now, I'm having a very hard time disagreeing with him on just about anything. In fact, he has been a source of inspiration for my work getting into flu forecasting and epidemic forecasting in general. And every time I thought I was coming up with a new exciting observation, I found out that Jeff has already come up with it before. So rather than trying to find fault with his work or ways of improving, I want to try to instead just use a few minutes to build on it. My sort of share with you my take-home messages from this talk. My number one high-level take-home message is that the bottleneck in our work in general, and specifically during this pandemic, is not in the science, but in the data. Jeff and I have talked about it many times before, so I know he agrees, but I think it's worth saying that this is a case, which is not necessarily the case in other disciplines. This is a case where the science far outstrips the available data. Which is kind of both a good and a bad thing. It's a good thing in the sense that getting more data is more of a logistic problem than a open-ended problem, but it's bad or sad in the sense that it's a very difficult logistic problem we haven't solved yet. One thing that sets apart, if you think of forecasting epidemics versus forecasting weather, and I know that Jeff has come from the world of forecasting weather, so you appreciate that, is in forecasting weather, meteorologists and other people who work on it don't need to worry about what the past or the present are. They are free to focus on what the future will be. In epidemiological modeling and forecasting, knowing what the present is a big open problem. And knowing what the past, the near past was, is an open problem. So there's tremendous uncertainty in epidemiology because of the difficulty of measuring the important elements. And to me, if there's one most important take-home message from the way the current pandemic was handled, at least in terms of its modeling and understanding and forecasting, is that we need to revamp our surveillance significantly, qualitatively, not just quantitatively. We need to think of completely new ways and new orders of magnitude of collecting data so that the work like the one that Jeff described can be carried out weeks earlier, if not months earlier. So what kind of surveillance do we need that we don't have now? This is an open question that I would love to discuss here. I would love to hear what Jeff thinks about it as part of this discussion. I can share some things with you. I think we need some ongoing random testing. That's not, a surprise. We need sentinel testing. We need people. So the random testing of the kind that Jeff described in the clinics in New York. We need to do it all over the world. But we also need the sentinel testing, people who agree in advance to be tested regularly and to report their symptoms regularly. Now is a good time to sign up such a sentinel army, because now, I mean, I'm sure Jeff feels the same way. All of a sudden, the whole world agrees with us. All of a sudden, the whole world realizes the dangers of epidemics and the need for collecting data and managing them better. So the iron is hot, and now is the time to set up such networks and get people to commit to participating in them. We need more serosurveys. I think Jeff touched on that at the very end. We need more measurements of levels of antibodies that people have in their blood as a measure, as an indicator of how many people have had the specific illnesses, whether symptomatic or not. So these are just 2 or 3 elements that are sorely needed, in addition to a variety of other elements, what we call digital surveillance, where we look at people's purchasing behavior and work behavior and the mobility data that Jeff mentioned and so forth. To collect all of these and make it useful, we can't afford to do that as a new pathogen emerges. And then scramble to stand up a system. This is my second take-home message from this year of 2020. Quote somebody who gave me this advice: the system that will be useful to WHO, CDC, and everybody else in the next pandemic is not the system that we will scramble to set up at the beginning of that pandemic. It is the system that has already been set up before and has been used on a regular basis in the interpandemic period. So systems that have been stood up and are operational all the time. My personal experience, or our group's experience, has been that we were running around frantically trying to be useful to various public health groups whose needs were changing every few weeks. And as you build their model and create something and some forecasting capability for them, by the time the model is up, it takes you 24/7 work, a month or 2. And then by that time, their needs change and the situation changes. And so the time to build the system is not during the pandemic, it's before the pandemic. The other type of comment I'd like to make is about the distinction that Jeff made between inference and forecasting. I was very glad to see that he was focusing on inference. And the reason is both Jeff and I have worked on forecasting specifically in the context of flu for many years. When it comes to a pandemic, I personally find forecasting to be very problematic. And very risky in terms that it's very open to misunderstanding and misuse. And the reason is pandemics in their nature are one-off events with very unusual circumstances, unique idiosyncratic circumstances. When you come to forecast something like that, there's very little data to rely on. It's not so much a problem for building a model. It is a problem, but not as much of a problem building a model. It's a bigger problem for validating a model. So our experience has been that you can, let me give you a thought experiment. Suppose you build a wonderful forecasting model for a pandemic, and suppose it really turned out in eventually that it made great forecasts. But at the time, you had no way of knowing that it would make great forecasts. So you cannot rely on it. The only way you can rely on forecasts is if they have proven themselves before. And that can happen only when you have repeating events with some amount of regularity where you can validate and build a track record. We have done that for flu, both Jeff's group and my group. Over years, you build a track record, you build average accuracy, and you can develop some confidence in it. It's very hard, if not impossible, to do for pandemics. One other complicating factor is that in a pandemic, you're not only modeling the virus, you're modeling people. We can kind of project maybe a week or 2 or 3 forward what things would happen downstream from our early indicators. We know that if there are new infections happening today, they will result in some positive test case in a short while and will result in some hospitalizations and some deaths and so forth. That is fairly predictable. But what we cannot predict with any level of confidence is how people will behave, how governments will behave, and how will people will react to government's behavior. I think humanity as a whole has a terrible track record when it comes up to predicting human behavior and societal behavior. And this is certainly not my area of expertise. So for that reason, I think the inference work that Jeff did is excellent and very useful. If we had better data, he could have done his work weeks earlier and saved us, multiple weeks and made the result more actionable. But I would be very careful about putting any stock in forecasts of one-off pandemics for more than 2-3 weeks at a time. And I'm so glad to see Jeff nodding his head in the right direction. And I will stop here and open it for discussion. Back to you, Lily.
Thank you so much, Ronnie. I appreciate the discussion. I like your discussion about the collected data, survey, and also surveillance systems. Also appreciate your insight about inference and forecasting the pandemic. So Jeff, now I'll turn over to you. Do you have anything to say in response to Ronnie's discussion?
Well, I think Ronnie and I really are in agreement on it. I won't even call them forecasts at this point. I call them projections. They're based on, they're all conditional probabilities when you think about it. You make a projection in the future and you have to have some assumption as to what society will do. Look, the thing that allows people to make numerical weather predictions and have the system work successfully is the system is stationary. The laws of physics governing what's going on that they're trying to predict are pretty damn immutable, right? The thing that allows us to do seasonal flu fairly well, not as well as weather at this point, is the fact that it's fairly stationary. How people have responded to the threat of seasonal flu each year has been relatively stationary. People who get vaccinated, the people who don't get vaccinated, don't get vaccinated. We don't close schools down. We don't have people wearing masks in response. We don't have policy questions. For something like this, we have so much disruption of society. And as Ronnie pointed out, it's an entity for which we really never modeled it before, that you're stuck with having to say, well, we have some estimate of maybe what its behavior up to date has been and what its properties are. And if we're going to project that into the future, first thing you have to do is make an assumption. Well, are we just going to continue doing what we've done over the last few weeks? Or is some new policy going to come in place? Are people going to wear masks more? What's the level of compliance? The difference is in the reproductive numbers that I showed early on, which are even more marked if you look at other counties and other parts of the country that did nothing. If you look at North Dakota, for instance, even in the run up to their huge wave they had, and they've had more per capita infection there than any other state in the United States. If you look at that, it's variable. It's highly variable, and it's I don't know how to predict it. So I think you're stuck with these projections. I've had some very strong disagreements with some others in the infectious disease forecasting community about even calling these forecasts, because I just don't think they qualify in some basic way. Now, the data issue is enormous. It is the critical reagent that we need to have better data on. And I'll give you a really good example of where, if you happen to have data, it can work well. We know about this UK variant that's out there, and it is a variant of real concern because It binds better to the ACE2 receptor. It's more infective in the laboratory and cell lines in animal models. And epidemiologically, it appears to have supplanted the previous variants in circulation in the UK and has a considerably higher reproduction number, meaning it's more transmissible. Well, did it emerge in the UK? Probably not. Why does the UK know about it? Two reasons. One, they sequence more than any other country in the world. They've been actively engaging in trying to document and keep track on this better than anything, much better than the United States. Secondly, they had a happy accident. They have a standardized test that they use diagnostically, the PCR test, to tell if somebody has the infection or not. It's a PCR test made by TACPath that, for the old variant, lights up 3 bands that are 3 portions of the genome of the virus that are amplified. And it so happens they lucked out, you could call it luck if you want, that for this new variant, only 2 of the bands light up. So they happen to have, through happy accident, a ready way of telling whether every individual who tests positive for this virus has the old variant or the new variant of concern. And because of that, they've been able to make a very meaningful analysis of this that tells the world what we're dealing with. They've been actually able to estimate how transmissible it is in actuality and the problem that we may be facing in the coming days and weeks and months in the US and other countries around the world, should that virus take foothold and really take off. That's the advantage of being able to observe systems. It's very challenging to do so, but I like some of Roni's ideas about trying to get a whole group of people that are willing to provide the type of information, something like what we collect in the Virome project. I mean, look, ultimately you can get very high tech or Star Trekky about this and say, and I joke about this, that at some point in the future, people will get up, they'll breathe into their cell phone and it'll tell them what they have. And it'll report it to public health authorities because we'll have all the appropriate sensors there and we'll be able to keep track of respiratory infections. And then the follow-up, of course, is, 20 years after that, the phone will spray you in the face with a monoclonal antibody and you'll be cured and we'll be done with it. But we're not there. We're not nearly there at this point. And so we need to really make the investment in better surveillance and open up some of the records that are being hidden behind corporate privacy so that we can actually get a better understanding on what's going on with these pathogens. And now, given everybody's sense of urgency about the problem, maybe the unfortunate but opportune moment to make that happen.
Thank you so much, Jeff and Roni. I think we all learned a lot from your insights and discussions about the epi models, the effect of data quality and on the projection and also the surveillance. So maybe we have 10 minutes left. We'll go ahead and take some time for questions now. Just a reminder, please be sure to type your questions into the QA panel. So here is the first question. So I think from your presentation and discussions, we can see that epidemic models hold the key to understanding the course of the epidemic. Especially in Professor Shaman's talk, we have seen that modeling and simulation have a major role in understanding the spread and growth of COVID-19 incidents. And we also see there are so many epidemic modeling methods nowadays, from mathematical models to statistical models to agent-based methods. So there are so many models to choose. So can you both give us some suggestions on how do you choose the most appropriate model? Jeff, I'll start with you first.
Sure. So there are lots of modeling options. I mean, I strongly favor in types of problems such as this and situations, you build the model to the system. You don't just go off the shelf with what you have. I favor model parsimony. It maybe seem a little ironic to say that, having shown you the model I did, which is actually gets fairly higher dimensional. But what it means is that I'm not as big a fan of agent-based models. I think that trying to specify what individual actors within a landscape are doing, even if you argue that, well, the emergent properties of the disease will come out at the macro scale, I still have a problem with thinking about all the micro scale processes and what it means. So I favor models, even though they have misspecification issues, that are compartmental and simple in their basic construct when I want to look at things dynamically. You know, and what you couple with and how you work with the system is always a level of inquiry. The thing that's been interesting over the course of this outbreak, of course, is the number of people who've jumped in, who wanted to contribute and help with the understanding of the field, which is great. And it's produced an onslaught of information, some of it good, and frankly, some of it very bad. And so it's, you know, if you're going to go into something, obviously you want to be aware of the circumstances in the field that you're jumping into. And that's always something that each of us has to hold ourselves accountable for dealing with. But I think the thing that's been nice about it is we begin to see even more methods brought to bear. And I'm not aware of all of them necessarily, and I haven't had the time to read all of them, but there may be some new avenues and streams of cross-pollination that ultimately are going to further advance the field that will come out of this, because so many people have joined in trying to solve this and help out.
Roland, do you have anything to add to the model selection?
Yeah, to that question. So I generally agree with Jeff. I want to try to make a distinction between models for scientific understanding and models for forecasting, which I view more as a technology than a scientific endeavor. My own group, the Delphi group, our focus is mostly on building the technology, although we acknowledge that in the longer term, the better science you have, the better the technology will be. But in the shorter term, there's a huge distinction between the two, because if your goal is to understand what's going on and to explain it, you may be led to a more generative model, a more simplified model, like Jeff was suggesting, a smaller compartmentalized model. If your goal is to make the best possible forecasts, then whatever produces the best track record of forecasting is probably going to be preferred. And we have an example from the last 8 or so years of annual forecast of flu, where our group has, as you mentioned, has done very well. And I think we've done well with a model that had very little sort of scientific or generative story in it. It was much more focused on a sort of machine learning approach of a time series. And I think it did well because of the amount of data that was available. We had 20 years worth of data of flu to train on. This is the other big factor. Ask yourself what kind of model you want to use. How much data do you have? The general rule should be that you should make as few assumptions as the data allows you to make. Namely, the more data you have, the fewer assumptions you should make, the less you should rely on assumptions, because as we know, all assumptions are wrong. But if you have very little data, you must make some assumptions. Of course, in the case of a pandemic, we have extremely little data. We have no historical depth, namely no previous seasons to look at that are directly relevant, or very, very little. We have some geographic depth in the sense that we can look at what's happening in many different cities, many different metropolitan areas, many different countries, although we have to realize that many of them are correlated. So correlation across geography in the context of pandemics is very high, which means that the actual bit rate, the actual amount of truly independent information we get from the pandemic is relatively small. So we cannot afford to make, so we don't have a choice. We have to make stronger assumptions. It's useful to maybe classify models differently. One family is what we call mechanistic models. This is what Jeff was referring to as models that make assumptions. And within the mechanistic models, you have one extreme is the compartmentalized models, which make relatively few assumptions that all epidemiologists know are gross oversimplifications. And in the other extreme, you have the agent-based models Jeff mentioned. These are the simulations of individual people that can make arbitrarily complex assumptions. Where you fall in between those, I think, should depend on how much data you have. And to me, the main issue there is the ability to fit the parameters. Jeff showed us a very, very nice, very neat demonstration of fitting parameters and demonstrating that the model is identifiable. That should give us some comfort with regard to finding the right parameters, but it doesn't give us comfort with regard to validating the model itself. It's identifiable within that model family, but it doesn't quite tell us whether the model family is validated as suitable. In the case of a pandemic, what was a suitable model this week may not become maybe a non-suitable model 2 weeks from now, making it very difficult. So I don't have a magic answer. I just wanted to lay out the different types of models. In contrast to the mechanical models, we have the non-mechanical models, which is what our groups have been using, our own group, Delphi group. And then the last thing I want to mention is something that Jeff mentioned earlier, which is the assimilation models. I think they are probably the future of epidemic forecasting, at least. So these are the models that have been used for many decades in the weather forecasting community. And basically what they do is they try to compromise between the model and data. There is a model, but the state of the system keeps being adjusted by measurements. So they go through alternating steps of progressing the system based on the model, the process model, and then adjusting the state of the system based on actual measurements and accounting for noise and uncertainty both in the process and in the measurements. To me, this is sort of the best marriage of the two worlds, and I'm guessing this is where everything will be heading eventually.
Thank you so much, Jeff and Ronnie, for the model selection insights. So we are kind of running out of time, and we see so many questions in the Q&A. So there are some technical questions for Jeff. I think maybe I'll ask the audience to send you an email. You can try to answer later because there's so many of them. So we have like 1 or 2 more minutes. So I'll just quickly go to the end. So thank you so much for the helpful suggestions. So if there's one thing you would like the audience to take away from today's webinar, what would it be? Jeff, I'll start with you.
Well, my message will be a public health message, and that is one not scientific. I think I'm compelled to tell everybody that while the vaccine is being rolled out, we have and that might be a light at the end of the tunnel, we have a long way to go. And that we need to get a lot more vaccination distributed and into people's arms before we should seriously be considering a relaxation of all the non-pharmaceutical interventions that we have in place, inadequate as they are. If we give those up too soon, more people are going to be infected and die from this virus before they get the vaccine.
Ronnie.
I would say there are many ways in which we haven't dealt with this pandemic optimally. Now is the time to learn from it. And from my perspective, the biggest one is we need to make a public's voice known to government that we need better data, that we need somebody in the chat was asking, why don't we have better data like they do in economics, econometrics? And the answers are privacy concerns, as well as who owns the data. In the US, the data is owned privately. Much of the data is owned privately and in a very fragmented way. And we need to find public policy solutions to these problems.
Thank you again, Jeff and Ronnie, for answering the questions and for great presentation and discussion. It was a pleasure to have both of you with us. If you want to learn more, mark your calendar for every first and third Thursday afternoon from 12 to 1 p.m. Eastern Time. So with this concludes the webinar. Thank you all for attending. We hope you have learned and enjoyed the webinar.